Hi.
Hi. All right, so we're waiting just a couple seconds until everybody else gets here, but welcome. They should be coming on soon.
I don't know how I did on the test. I thought I did well because I studied a ton for it. Like I rewatched the videos and looked at all of the practice I done on it. But they were gonna have to take points off because I did not see the homework that you posted on Edmodo, and I didn't do it.
Hang on. What?
I can't really talk. It's messing up. I don't know how to fix it.
I can hear you just fine.
You can understand what I'm saying?
Uh-huh.
Okay. I didn't do the homework. I didn't see it until a few minutes ago on Edmodo. I had thought that you would have told us about it, so I didn't check.
Okay. I told you guys on whichever day it was that I gave you the test, which I think was a Tuesday, that you'd have to do the next chapter sections before, and so I posted it just so everybody would have it as a reference. But I did give you guys the heads up before, but we'll get on the same page. Jordan is the only one we're waiting for, so we will. Let me check in with everybody. So,
Stupid.
Okay.
So Emily Carr, checking really quick again. First, you are done with your test, right?
Yes.
Good. Thursday we are meeting in person, so I'm going to expect you to be bringing that and giving me that on Thursday. Second, I know you told me that you didn't watch the videos yet, but when we're done here, you can go and watch those and do the reading, so you'll catch yourself up. Emily Mongold, checking in with you. Before you went on your trip, were you able to take your test? Also, the quiz wasn't that great for you. I don't have your work though. So I may have I graded it harshly because I didn't have the work, and I may be able to give points back on this particular quiz because
this test and quiz were terrible.
Okay, no.
I can just tell that, and it keeps freezing, so
I can still hear you. You're okay.
Okay.
All right, really quick, Emily. I don't want to scare you, but the process that we learned in this chapter, stoichiometry, it is going to be used for the rest of the year. So if we need to have a couple one-on-one sessions or do something, you gotta get it. You're not gonna make it this year if this isn't something that we shore up. And I do understand, and I'm really sorry. I know that it's been a really hard last several weeks. Like you've had a tornado, earthquake, hurricane kind of month, okay? So I'm not as surprised that it was a more rough chapter. I don't think it's because you don't think you don't have the ability to do it. I think it's just that your mind's not been as focused on chemistry, which is
not a good thing.
Given everything that's going on, it's not surprising, and it's not something I'm not going to sit here and try to beat you up, okay? I'm going to try to go, all right, so maybe it wasn't that great. Let's build from there, and let's make sure that you don't miss the things that you're going to need to be successful in this class the rest of the time, okay? So I would like to maybe Sunday, can you hang out a little bit afterwards? And maybe
I won't be here on Sunday.
Okay, so we'll just talk some other time. We'll get a day, okay? But I would like to try to just make sure that it's something that you get. I know there were several videos where you couldn't be there. You know, things were going on. I get it. So let's just try to go from here and get some support for you, okay?
Thank you very much.
Were you able to watch any of the videos for this next chapter at all, or read any?
All three. The 3 videos were due today, right?
They were supposed to be due today, yes. So, but I mean, I didn't actually post that until either Sunday or
it was yesterday
or Monday. I was trying to say
yesterday.
But So you guys just make sure that you get that taken care of, and good job, Emily, on making sure you did take care of that. I still don't know where Jordan is, so I'm gonna, I don't know. All right, so Emily, your mom was checking in, but I'm gonna text and see if Jordan is able. All right, so this chapter though, guys, are you ready for a little bit of a break?
Yes.
Is it going back to like the energy stuff though that we learned in the other chapter?
We are going to come back to it, yes.
Yeah.
Like I said, the stuff that we were supposed to learn last chapter is gonna, like, literally, I'm in chapter, what, 14 or, no, 15. We just took chapter 15 test in my other class, and they're still using the stuff you learned in chapter 11.
Okay.
Like, and I'm telling them, remember when I told you that you better learn this in chapter 11, and if you didn't learn it, you better come in and see me? Yeah, that's because it's here, and it's the rest of the year. So I promise you, even though this chapter is going to take a breather, you're going to get to go, whoo, no more stoichiometry right now. It will be back. Okay? So you can't forget about it.
On Edmodo, you posted that the test was going to be soon.
The test was going to be what?
Soon.
Soon. Okay, yeah. So here's the deal with this chapter. This chapter, even in my normal school, I took a week. That was it. 1 week. They went through the whole thing. It is pretty much stuff you know from living in the world every day. Solids, liquids, gases.
Mm-hmm.
You've been learning about the difference between a solid, a liquid, and a gas your whole life. So we are not going to take an incredibly long period of time going through and teaching you something that you've had experience with for your whole life. We're just going to focus, though, and here's where it's a little different. Even though you've had contact with solids, liquids, and gases your whole life, and you've probably touched in many other sciences on the differences between them, now we're going to, because we're in chemistry, we're going to focus in on the molecular differences. What are the atoms doing? What are the molecules doing in a solid, or in a liquid, or in a gas? How are they different from each other on a molecular level? And so that's what we're learning that's going to be new. But the nice thing is that, I mean, there's not as much math in this chapter, if I remember right. It's mainly just the broad concepts. You are going to be doing a project over this. It's going to be a PowerPoint presentation where you are going through, and that's what I was looking for actually after I had started the video, was my directions. I have to find if I posted them on Edmodo or OneNote. And if I posted them on OneNote, you guys don't have access to that. So I'm going to have to get them and send them to you. So I will send that as soon as I find it. And wherever I find it, I'll copy and paste it to you guys. Okay, so you are going to be making that project. And essentially, you're just going to watch the videos. You're going to do the reading. You're going to work on the project. And then you're going to turn the project in and do your test. And that's pretty much it. Today and Thursday, I'm going to touch base with you guys because some of you are having already watched the videos and some of you haven't, and Jordan's not here yet. It may not be as productive of a lesson today, but we're going to do the best we can, okay? And then we're just going to, pretty much you're going to self-pace and you're going to just handle the material. It's the reason I wanted you to do a project on this one, is the more you put it in your own words and present it, the better you're going to be at it. Okay? So essentially the PowerPoint is going to do the three main areas. You're going to go one, solids, liquids, gases. And you're going to use the kinetic molecular theory, which, think about the words in that. Kinetic, what does kinetic mean?
I don't know.
Like, just words. Where have you're like kinetic energy and stuff like that, so that's the energy of what?
Water.
Motion.
No, to move.
Motion.
Word to move.
That makes sense.
Yes, to move, kinetics, right? And then molecular, so we're looking at the
Molecules.
molecules. So it's how are the molecules moving? It's a theory of how molecules exist. Now, the kinetic molecular theory is mainly applied to gases. And it's going to have a couple main ideas, but even though it's mainly focused on gases, you can kind of extrapolate that out to the solids and the liquids and just focus on the motion of the molecules in a liquid and in a solid. Okay, so see, although the book only focuses on gases there, you can still focus on the motion of the molecules in a solid and a gas, in a liquid. Okay, so that's what we're going to be doing. So the 3 main points, if you guys want, you can use your book and look at page 403, where I'm going to be, page 403.
Oh, you mean the
I'm going to call Miss Lane and just see about Jordan because it's been 17 minutes and I am getting a little nervous. So I will be telling you guys as we go. I want you to look at the 3 points: particle size, particle motion, particle energy. Read those 3 paragraphs for me and be ready to talk about it when I'm done.
Okay.
Okay.
Finally.
Hey, Jordan.
Hey.
All right. Jordan, you're going to have to go back and watch the other parts of this video after we're done, okay? So you're going to need to catch up to this point. But first I'm going to ask, did you take your test already?
Yes, I took that before I left for PCC.
Okay, good. I want you, all 3 of you, to bring that test on Thursday with the work. And also do me a favor and bring the work from the quiz over that chapter 2, because I graded them without seeing the work. In some of the cases, I may have been able to get partial credit because you may have set up the problem and just flipped one of the conversions. And I had to take off all the points because I couldn't see that. So I need the work for the quiz and the test with the work for the test, okay? So bring all of those things on Thursday. Jordan, were you able to watch the 3 videos that were due today?
I was able to read the 2 parts from the book, and I was able to watch 12.1a and take notes on it.
Okay.
I have not been able to watch the other 2.
Okay, so what you're going to have to do is finish those other 2 videos, and then before Thursday, watch all of the videos for what's due Thursday, okay?
Okay.
Did you read the part in the Edmodo about the project that you guys are going to be doing this chapter?
Yes, I saw that. I wasn't able to look too much into it just because I had a lot of other schoolwork I was getting caught up on. But yes, I did see the PowerPoint project thing.
Okay, so look, I haven't gotten the directions to you guys yet. I have to see where I put them, whether I put them in Edmodo or whether I put them in OneNote, and then I'll find them and post them to you guys before the end of the day.
Okay.
All right, so So, ladies, you should have had enough time to finish those 3 paragraphs. Jordan, we are starting on page 403. We're just going to talk about the kinetic molecular theory and what we're going to be doing with it this chapter.
Okay.
So what are the 3 parts of this kinetic molecular theory? We're all on page 403, and we're going to look at those 3 main areas of the science behind how the molecules are moving. All right, so Emily, what's one of the points?
Which one?
Thing 1.
Okay. One of the points is particle size. Is that what you're talking about?
Yep, particle size. Okay, so look. Are gas particles large, small?
Small.
Incredibly small. And so they are zipping past each other like this. Crazy, right?
Mm-hmm.
Is there, in that paragraph, is there essentially going to be attractive forces between these particles as they zip by each other, or no?
No.
Good. This is a difference. And the main thing about your PowerPoint is you're going to be comparing and contrasting, right? You're going to be trying to show this is what a gas is. This is what a liquid is. This is why they're different. Gases are the only one of the 3 that have virtually no intermolecular forces. Okay, so that's really important to know from the first part, particle size. Jordan, we also were talking before we got into this about, even though the kinetic molecular theory is really focusing on gases, we are going to kind of refer to it even when we're talking about liquids and solids, because we're still going to focus on the motion of the atoms, molecules, and ions.
Yeah.
So we are still going to kind of, but some of this only applies to gases, but we are going to think in terms of how are the atoms shaped? How are they in a crystal lattice? Are they locked together, or are they free flowing? Or so we're thinking about the motion and the structure. That's where we're really focusing, okay?
Yeah, the next big area is particle motion, and particles, they go in a straight line unless they collide with the container that they're in or with another particle.
Good. So think about this, guys.
I mean molecule, sorry.
Yeah, that's fine. Think about if you have a pool table, right? Can everybody picture a pool table in their head?
Yeah.
All right, so after the break, the balls are all over the table, right?
Yeah.
Let's say you take the cue ball and you hit it straight. What's going to happen to that cue ball?
It's going to bump into the other balls.
There you go. It's going to travel. Is it going to go in a zoo, 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 zoo line?
Hopefully not.
What's it going to do?
It's going to go straight, and whatever it's in its path is going to collide with it.
There you go. It's going to go straight until here's another ball, and when it collides with it, what's going to happen?
It's either going to stop or go in a different direction.
There you go. They're both going to be affected, and they're going to ricochet, right?
Mm-hmm.
That's what gas molecules do. What if you don't hit any of the balls, and instead you hit the side of the table?
It's going to ricochet. The same thing.
Ricochet. Same thing, right? That's what a gas molecule does. It's zipping around until, let's say, the gas molecule hits the wall here. It's going to go boom and bounce off, all right? What's important with this is for gases, these are considered elastic collisions. And I want you to try to think about and put in your own words, what does it mean to be an elastic collision? You can use the pool balls as an example of an elastic collision. That's fine. You can use those to describe it. Go ahead, Jordan.
With an elastic collusion, sorry, it doesn't gain or lose any energy.
Okay.
So I guess with I don't know, it's kind of hard to think of with a pool table. Okay, so say that you hit the cue ball and that hey, is it possible to turn on the mic on your end? Because it's like echoing and throwing me off.
What?
My voice is echoing and it's coming through on my headphones, and it's just like throwing me off a little bit because I'm hearing everything that I say a second later. There we go, that's better. Okay, so with the pool ball, it actually, so say that you hit the cue ball, there's nothing in its path, and it just keeps going, doesn't collide with anything, doesn't, I don't know, I really can't think of a good example with elastic collusion.
We can't hear you.
Okay, so what I did when Jordan asked me to try to take care of the sound is I had to mute it, and I didn't know if that meant that it was muting for everybody, if I was being muted. So I guess we're gonna just have to deal with the echo because I can't have you guys, I can't mute you the whole time or you won't hear me. So here's what I'm gonna try to say. Think of the pool table and the ball, and remember the cue ball is coming towards this other ball. When it hits, think about energy. Energy is usually measured in like joules. So we're gonna just, I mean, to you right now that doesn't mean anything, but it'd almost be like me saying, you know, this unit of energy, all right? So if we have 5 joules when they hit, what's gonna happen to this ball?
Is this kinetic energy or elastic collision?
Yeah, so we're thinking about an elastic collision. So this energy is, this ball is gonna do what?
Are they going to transfer?
Yeah, it's gonna start moving. It wasn't moving before, it had 0 joules of energy. When this hit, it gives it some of that energy, right? Let's say this moves off on this side and this moves off this way. Between the two of them, let's say that this one got 3 joules of energy. So it's moving off with 3 joules. How much energy would this one have?
None.
It's
3
still
joules.
moving.
Sorry.
Huh?
3 joules.
Well, look, it can't go over 5. It had 5 joules, right? When they collided, it gave this one 3 of the joules. Now this is moving off in this way. How much energy? It's moving off with how much?
Jordan, we can't hear you.
Did you mute yourself, Jordan? You're not muted on my screen, so it must be on your end.
Take off your head.
Can you hear me now?
I can hear you now. Okay, so go ahead, Jordan.
I was saying a good example of probably the elastic energy would be those it's that stand that has like the string of 4 or 5 balls on it. You pull one back and when it hits the balls, the one on the opposite ends moves at the same speed.
Yeah.
And they go back and forth. They have the same amount of energy.
Yeah.
So I thought that would be a better example of elastic collusion.
All right, but we're going to go back to my example. When they collide, if this one gives this one energy, it loses that energy. It has given away 3 joules. Guys, what is 5 minus 3?
Oh, 2.
It's 2. It's not. It's 2. So this one has 2 joules of energy. All right? Look, the term elastic just means overall it didn't lose any energy, right? Between the 2 of them, they will equal 5 joules of energy. No energy was gained. No energy was lost. It was transferred from the one to the other. Now think about this situation. Ready? And Emily Carr, I want you to talk in this one because you have sat quietly for the last like maybe 10 minutes. So ready? Same situation, a pool ball. I'm only going to use my fingers this time. Okay? The pool ball goes, it's got 5 joules of energy. It hits this one. And instead of them both scooting off like this one goes, it hits. This one's the only one moving. So this one has how much energy?
5.
That's
5
all.
joules. And this one has now 0, right?
Yeah.
So then in another situation, if this goes, boom, 5 joules of energy before, now it gives this one 1.5. How much energy would this one have?
3.5.
No, let's not do halves. This gave 1 joule. Now how much does this one have?
None.
It gave it
That was
1.
still.
And now I changed the example, Emily.
Sorry, he's freezing.
I'm on the next one now. Oh, got it. I'm sorry. All right, so now another example. It's going. Hits it with 5 joules of energy. This one has 1. This one will have
4.
4. The only point here is that between the 2, they have the same energy overall.
That makes sense.
None was gained and none was lost. Now look, in real pool, it's not perfect because think about the table. The table is rolling on, the balls are rolling on the felt table. That's causing friction. So some of the energy is lost to the friction there, right?
And it can sometimes be on an uneven plane. So it causes it to either slow down or speed up.
Yeah. So there's a lot of variables in pool, but we're just using that as an example to help us think about what gas molecules are doing. Okay? So the gas molecules are constantly colliding, and essentially they're going to collide with no friction, with no loss of heat due to the waste there. That's what the elastic collision means. There's no waste of the energy. Go ahead, Emily.
If two hit each other like that, they'll bounce off of each other, right?
Yes, ma'am.
Won't,
So
they, won't they lose energy then? If they're going at each other, won't they slow down after they bounce off?
In pool, yes, but that's because there's waste. There's waste of energy. So sometimes, look, if you have two things colliding like this, in pool, they will slow down and, you know, because, well, think about it this way too. It's force. I'm pushing this way with 5 joules of energy. You're pushing this way with 5 joules of energy. We cancel each other out and we equal 0 because I'm going this way, you're going that way.
Exactly. And then energy has been lost, 5 joules.
Yeah. But where that energy actually goes is it'll go into heat with pool. It'll go into friction on the ground of the table. It'll go into sound. Like all of these things actually cost energy. And the reaction, because they were opposite, they're actually taking the energy to stop the momentum. The point is, the gas molecules won't behave like the pool molecules because they're so small. The pool balls are way bigger and they have friction. The gas molecules will just boom and bounce back the opposite directions.
Cool.
All right, so the last thing on the kinetic molecular theory, so there's particle size, teeny, teeny, tiny, right? Pretty much no attractive forces between them, which is why there's also like no problems with like friction or things like that. Next, particle motion, constantly in motion. If they go, they're going to go in a straight line until they collide and then ricochet, right? Elastic collisions, no energy lost. The third point is what?
Particle energy.
Particle energy. Now look, the energy can be measured overall, but think about when we take a temperature reading on something.
I thought this could be associated with like a thermometer because it causes the mercury to rise as the temperature gets higher.
Yeah, that's actually what we're talking about is when you put a thermometer into something, what's going on? And what's going on, let's say we are taking, because liquid is something we're more familiar with, liquids and solids. Say I have this and I put a thermometer inside of it, right? Mm-hmm. Well, what's going to happen is there's millions and millions and millions of collisions are going on with the liquid from the Mountain Dew and the thermometer. Mm-hmm. And they're bouncing off of it. And what happens is each and every collision is going to impart a certain amount of energy. Mm-hmm. The thermometer takes the average energy and it'll increase by that much or decrease if it's reverse, you know? And so that's why the thermometer increases or decreases. The same thing happens with a gas sample when you are taking the temperature of a gas. To put the thermometer into a gas, the gas molecules are going to collide with it, like they're colliding with the sides of the wall and with each other, right? When they collide with that, they're going to either give it energy or lose energy to it. Usually it's going to give it energy, and it'll adjust the temperature of the thermometer with the same amount of energy. So the main thing here that they're trying to get you to see is that temperature is an average of all of the molecules. It's going to be the average energy that they all have. That's what's going to read on the thermometer. So that's how temperature works. All right. Do you see how next they're going to explain the behavior of gases with this? And they're going to do a lot of things. We do have, okay, so Emily, I'm sorry, I did misspeak earlier when I said there wasn't a lot of math in here. I do remember there's a couple of equations. I think that these are some of the only ones, but there are two that we're going to have to work with here, okay?
AE equals 1/2 mv squared. I think it was one of them.
You're looking at the energy for the kinetic energy equation. We're not going to have to do math with that one.
Oh, okay. Never mind. Right,
turn the page now. All right. So they explain 3 behaviors of gases, and in your project, you are going to come back to these. Okay? So you're going to talk about density, you're going to talk about compression and expansion, and you're going to talk about diffusion and effusion. All of those are in your project. So I'm not as much going to spend time doing things that I'm going to make you research and make you provide examples for, okay? So let's just, between all of the things, gases will have high or low densities. What do you think?
Low.
Low. All right, actually, do you remember what density is?
Mass over volume.
Oh, that doesn't look like what it's supposed to look like. Okay, I'm going to try this separated. Hang on. There. Okay, well, it's separated, but do you see how this made a heart?
Mm-hmm.
M over V. Density is love or broken heart. I don't know. Density is mass over volume. So think about the mass of very, very tiny gas particles and how spread out they are. In a set volume, let's say I put a container like this and I fill it with a gas. What's the mass going to be for a gas? High or low? Very, very low.
No.
It's going to be very, very low because they were very light and not, you know, they spread out. They're not going to take up a lot of space, right? If I take the same amount and make it a liquid, right? So let's say we have this volume, we fill it with the same thing but a liquid. So it's completely full of that as a liquid. Let's just say water because it's easy because we think about it. We take this volume, water vapor. This volume, water as a liquid. This volume, water as a solid. Which one of those are the molecules closest together?
Solid.
As a solid. So guess what? Because it's got more particles packed together, it's going to have a higher mass for the same volume. So that's why solids are the most dense and gases are the least dense because they're spread out more. So there's less mass per volume. You guys are going to, in your project, be comparing these trends for solid, liquids, and gases. When you do solid, you're going to talk about density. When you do a liquid, you're going to talk about its density and compare it to the others, okay? So this is something you are going to put effort in. I'm not going to spend time here anymore, okay? So the next thing is compression and expansion. Have you ever had to compress air anywhere?
Yes. Sleeping mattress.
Sleeping bag or air mattress, right? So
Yeah.
in an air mattress, what are you doing?
You're pressing down.
You're pumping
Go
when you fill it up.
Oh.
Oh, actually, you mean after it's already done?
Yeah,
Let's
sorry.
talk about after it's already done. Okay, so we put all of the air inside of it, and we closed it. So none of the air can escape, right? And then you lay on it. You compress that gas, and it's able to move, right? The molecules can actually get closer together. Gases are the only ones that can happen for. It's important to know the difference between these. Solids and liquids will not compress. Okay, only gases are compressible because the molecules are free to move and they can get closer together and it's fine. Same thing in reverse. All right, so think about this. If you take, do you guys know like the containers of gas that you could have, like any container that's full of a gas?
Scuba diving tank.
Sure, scuba diving tank. Great.
Helium balloon.
Helium balloon. Let's do the helium balloon. It's probably more example that we're familiar with. Let's say we have a balloon and we fill it with helium, right? And we pop a hole in that balloon. Where is that gas going to go?
Go fill the whole room.
It's going to expand into the entire room, right? Those molecules, once they have an opening, they're not going to stay grouped together in the same shape, are they?
No.
They're going to go wee and like fill, and they're going to move out and spread out into the entire container, which will now be the room.
If you open a door, then it's outside.
If you open the door, it can get outside too, right? So they will continually be moving to expand to fill the container they're in. That is a trait that's unique also to gases. Filling the entire container, okay? So expanding and contracting, just gases do that. All right, diffusion versus effusion. That's a little bit where we want to spend some time. Do you guys know what the process of diffusion is?
It's when it spreads out.
It's when it spreads out. That's beautiful. Essentially, it's when you have particles that are going from a high concentration to an area of low concentration. So I want to paint you a picture. Let's say I'm making cookies. Where is the high concentration of cookie, like, you know how you can smell the cookies?
Uh-huh.
That's because those molecules are turning into a gas and floating around, right? Where would the high concentration of those cookie molecules be?
The cookies.
Wherever the cookies are.
In the kitchen, in the
In
snow.
the kitchen, in the oven, right? That is where you're going to smell cookies the most, right?
Mhm.
Why can you also smell them when you walk in the door?
Because they're floating
The-
everywhere.
It expands. The smell expands. I guess. I don't know. That sounds a
Through
little.
the process called diffusion. So what's happening is the cookie molecules, like think about this in the oven, we have them. They're constantly coming out. Shoo, shoo, shoo. They're constantly colliding with all the other gas molecules that are around them, like the oxygen that we breathe and the carbon dioxide and the nitrogen and all of those. They collide and they ricochet, and they collide and they ricochet, and they collide and they ricochet. And as they're doing that, they're going to eventually fill the entire house. So your whole house is going to smell like cookies, right?
Yeah.
Did you take a fan and blow it? Did you go on, gas molecules, get over here to the kitchen and to the living room and to the bedroom?
No.
No, it naturally moved by random collisions, right? That's diffusion. Going from the high concentration to the low through natural, just random bumping in and colliding and things like that.
Mhm.
Effusion, and I'm going to type it, effusion is the same thing, only through a tiny opening. So I want you to think of a tire.
Uh-huh.
What is something you never want to have happen to your tire?
Get a hole.
Get
You
a
never
hole.
want it to pop and get a hole in it, because what's going to happen?
The tire will go flat and then it'll call.
All right, before the tire goes flat, what's happening to make the tire go flat? All the gas that was
Inside leaves.
inside is now going outside. But is it going outside through everywhere in the tire?
No,
through the hole.
No.
Just through
the one hole.
the one hole. That is effusion. It is the process of going, look, inside the tire, there's a high concentration of air, right?
Right.
Outside of the tire, not a high concentration of that air. What's going to happen is it's going to naturally spread from the tire outward, but it has to go through the tiny little hole where you poked the hole in the tire. That's all effusion is. It is the process of diffusion through a tiny opening. Make
Okay.
sense?
Yes.
Okay. We're going to use this to do math. So, do you notice that there was actually a scientist, his name was Graham, and he studied different gases, and what he did was he took gases like helium and gases like carbon dioxide and gases like oxygen, and he put them in containers. And these containers, he had the same amount of gas in each container. And then he would poke a hole in it and see how long, he would clock it, how long did it take for them to empty out into the air.
That's kind of hard to calculate, isn't it?
Well, if you're looking at a balloon, you can see when it deflates, can't you? When it's completely deflated, all the gas is gone, right?
Right.
So that's, I mean, he was able to calculate how long it took for these gases to effuse, to go through the tiny opening, right? What is different about these gases? What makes helium helium, CO2 CO2, and oxygen oxygen?
What they're made of.
What they're made of. Look at the molar mass on your periodic table. How much does helium weigh?
Not much.
1.01.
That's hydrogen is 1.01.
Yeah. Oh, oops. 4.00.
All right, so 4.00 grams per mole, right? That's helium's weight. How much does oxygen gas, which is O2, how much does that weigh?
32.
32 grams per mole. How much does CO2 weigh, which would be, you know, oxygen plus CO2?
44.
Hang on, let me double. 40. Yeah, 44.01.
01.
01.
But I'm just gonna round it like that. So think about this. Which one of these is the smallest and wouldn't weigh as much?
Helium.
Helium.
Helium. All right. Helium, because it weighs the least, is easiest for it to escape. Carbon dioxide, because it's the heaviest, it's going to move slower. And it's going to take longer to get out. Right?
Right.
It's like if you were to take the same, like a person, not like if you have a wrestler versus like a chess clock nerd, right? Same physical fitness. And you put one of the people, nothing weighing on them. And on the other person, you put a heavy, huge backpack. Who's going to run faster?
The one with the lightest.
The one that's lightest, right? They're going to be able to escape the fastest. The one that's weighted down and heavier, they take longer to effuse. That's the relationship he found. So notice how you have the rate of effusion, and that little funny sign, which means is proportional to 1 over the square root of the molar mass. That's not necessarily the equation we're going to use when we do math. The equation we're going to use is at the next page, where it's comparing the rates of 2 different gases. So look at this. On page 405, rate A over rate B equals the square root of the molar mass of B over A. It's just as simple as this. You have to know the equation. You have to know which one's A and which one's B. Then you just plug and chug, and you're going to solve for the unknown. Okay? So first things first. Write this down. The first gas they give you in the problem will always be A. The first one you see, that's A. Next, remind yourself that the molar mass is reverse. Because every time, I guarantee, people forget to put the molar mass of A on the bottom, and they get wrong. It's reverse. Remember, don't make that mistake, okay? So you crisscross. All right, are you ready to try and work this problem?
Number 1, I'm guessing?
Number 1. Here we go. Listen. Calculate the ratio of diffusion rates for nitrogen and neon. First off, when they ask for a ratio of diffusion rates, you're going to set it up, and then you're going to get one number, and that is the ratio when you do your math. Okay? The ratio is always going to be one number. So I want to write this down so you guys can follow along. Hang on. There. Okay. I have the pen. So we're working with the equation right up there. Which one is A?
Nitrogen
or neon?
Nitrogen.
Why? You are correct, but why?
The first one is always A.
The first one's always A. So look, to start, we're going to put for the rate of N2 over the rate of neon will equal square root
of neon over N2.
Of neon's molar mass over N2. Now, go to your periodic table.
It's freezing.
We just had to plug in the molar masses.
Okay. So it's just N2 over Ne equals Ne over N2.
Yes. So now all you have to do is find the molar mass for Ne.
Okay.
And the molar mass for N2 and plug them in where they belong. So neon, if you look at your periodic table, neon is 20.18. That goes on the
Top.
top. Good. Nitrogen is
28.02.
Yeah, 28.02. Do you see how we crisscrossed these? This is important. Nitrogen is on the bottom. Neon is on the top. Now, quick disclaimer. For those of you that don't have a scientific calculator, I'm not sure I'm going to be able to tell you how to do square root on your phone or whatever. James may be able to help me with that, but this is what I'm going to have to use every time because I don't know. I'm sure there is a way to do it, and maybe you can look up YouTube or ask Google, how do I do a square root on my cell phone? There is a way, I know. I don't know it well enough. So here I'm going to type in how I would type it, okay? So you see how you have second, and then you push this button right here, which is the x squared? Right there. That's the square root. See how in yellow I can see x squared square root. See? So I push the yellow button, and then I push that button. Notice how it pops up with the square root sign? Inside the parentheses, I have to type in 20.18 divided by 28.02.
Oh. That's why I got that weird answer.
Divided by 28.02?
Yeah, and then I put the end parentheses, okay? When I push equal, that's going to be my answer.
And the ratio is 0.848645896.3.
Now, what I'm pretty sure you guys are going to be able to do on your calculator if you have it on your phone, don't quote me on this, but I'm pretty sure you can type in just on your phone 20.18 divided by 28.02 and then take that number, and there should be, in the scientific, when you turn it sideways, there should be the symbol for the square root. Push that button and then type in the number that you got, and it should give you the same answer. I just don't do it there. I use my scientific calculator, okay? So you may have to figure that one out on your own, but you do have to be able to take a square root, okay?
Okay.
Now, sig figs. There's not really a good basis for them. You see that? Look at the number. There's not really a reason to have them here, obviously. Or not a reason that's obvious. So just give me 3.
8, 4,
Anytime
9.
you do this, just give me 3, okay? Now, some of the problems may have a one that will give you a basis for sig figs, and then you can use it. But if it doesn't, like this one, there's no numbers in number 1, right? The numbers that you looked up for your molar masses, those are not able to be used. So if it doesn't provide a reason, just give me 3 sig figs. Does that make sense?
Yeah.
Okay. Now I want you to do number 2. Calculate the ratio of diffusion rates, which is the same thing, for carbon monoxide and carbon dioxide. Now, carbon monoxide, use your wonderful skills that I gave you earlier in the year. What's the chemical formula for carbon monoxide?
One is just 1, so.
So how many carbons?
1.
Oh, so it'd be just CO.
It's just CO. Good. And what's carbon dioxide?
CO2.
2.
CO2. Good.
So the first one, carbon monoxide, is just CO.
Yep.
Okay.
And the second one is CO2. Go ahead and do this with those and work through that one.
It was carbon and what? CO2?
Yeah.
CO2.
Carbon dioxide. Type your answer when you get it.
I'm so slow.
Oh, James.
So do I divide and then square it?
I would divide and then square it. But do that and tell me what your answer is, Emily, okay? And Jordan, you did something incorrectly. Did you correctly label A and B and then remember to flip-flop them when you did the division?
I'm sorry, I misread it when you typed it up there. That would be opposite.
I have, you want 3 sig figs?
Yeah, just give me 3 because there's no numbers to give you a basis, so just give me 3 sig figs.
I have 1.25.
Yep.
Okay. That's not hard. It looked hard.
Emily Mongold, how did you do?
I got 1.25.
Hang on, let me click on yours. That's perfect. 1 point. Yep, that's perfect. All right. Jordan, did you figure it out?
Yes, it was backwards, so I got 1.25. Well,
Okay.
25.
All right. So remember, the biggest thing here is correctly labeling which one's A and which one's B. Now, because I love you so much, I'm going to make it just a little harder. Not too much harder, but just a little harder. What if we don't want, because what you're finding is you're actually finding the ratio. You know, like if we had a number here and a number here, we would divide it and it'd be 1.25. Okay? That's the ratio. Now what they're going to have you do is look for a molar mass. Okay? So they're going to give you a rate here, and maybe a molar mass here or here, and ask you for the other one. Okay? So let's go ahead and practice one of those. Turn in your book to, hang on, I have to get there first. To page 434.
$4.34 or $3.44?
434.
4.34.
You know what I remembered?
What are you talking?
I remember that I hate the way that the book does these examples. I'm going to tweak this. We'll work with one of these, but I'm going to tweak it because I don't like the 3 times more or 3 times less. It always that confuses me. And when I give you these, I'm going to give you a real one. Okay? So look at 42. It says technically, what is the molar mass of a gas that takes 3 times longer to fuse than helium?
So we find out how long helium takes to fuse, and then we multiply it by 3.
Yes.
Yeah, it takes it a
You know, so you're doing just fine. But I was going to give you real numbers because I don't like the 3 times longer than. But yes, that is exactly how you would solve that. I'm just going to give you real numbers, though, and how do you use the real numbers. All
Okay.
right.
I have a question. I don't know how to figure out how helium fuses.
All right. So here's what I'm going to try to do with you guys first. I don't want exactly like for you to plug in all the correct numbers. I want you to tell me what is A and what is B. Okay? So we have an unknown gas, which will represent as X for our unknown. And we have which other gas?
helium.
Helium. Which one is A and which one is B? Jordan, I can't hear you again. Which gas is A and which gas is B? Start with that. Remember, it's rate A over rate B equals the square root of molar mass B over molar mass A. You have to correctly identify A and B first. Jules.
The mysterious gas is mentioned first, so helium is B.
So helium is B. Good job. So look, label that first. Helium is B, so put helium, just give yourself a reminder, and we have the unknown up here, so I'm going to put an X. X over helium. Now what's going to happen over here?
We're gonna put the mass of helium on top.
Mass of helium on top, and the unknown mass, which is actually what they want in the problem, is on the bottom. So I'm going to put my X that's a bigger X down here, and I'm going to put the molar mass of helium, which is 4.00. Do you see how even though I had an unknown gas, this had to be identified so I know that helium here goes on top because it's B. A on the bottom, B on the top. Because these are crisscrossed. Does that make sense why I took the time to do this first?
Mm-hmm.
Now, according to what Emily said, we could have just plugged in like 3 on the top and blah, blah, blah. I'm going to just give you some real numbers because in my test and my quizzes, I will give you real numbers. So let's just say the unknown gas. Hang on, let me type it in.
So So the molar mass is equal to how long it takes to diffuse.
Hang on. Let me finish this.
You say hi.
Hey, baby. There. Look who's saying hi. Hi. Say hi, Joel. You want my calculator? Let's not do that. Let's give you a controller. Alright. James, I'm gonna tell your corny joke soon. Pascal. Alright, hang on. I have to give him back. Will you?
Come here.
Okay, guys. So, what do you plug in where?
Helium on top, 4.5 on bottom. You divide and then you square that.
Hang on. Unknown gas is what? On top or bottom?
Bottom.
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 Helium is on the bottom.
No, with our terminal.
Oh,
Remember, it's A. X is A. The unknown is A. So the 4.5 goes where?
Bottom.
Underneath.
But top.
You switch them though.
Emily, you switch them over here.
Ew.
Yeah.
This has to be A on top, B on the bottom. A on top, B on the bottom. This is switched. Which one is the unknown?
4.5.
It goes on top. Because it's the rate. Look at the equation. Rate A over rate B equals molar mass B over molar mass A. The molar mass is what switches, not the rate. It's right there in the equation. Go look at it. Now, what's helium's rate?
4.0. Oh, at 30.0.
30.0. All right. Remember?
How do
Emily, I'm fixing this because I didn't want you to have to.
you know that?
James, do you want me to move or would you guys be?
Yeah.
It's just.
Come here. Come here. We're being kicked out.
I'm sorry.
We know we're not one.
This is really hard to teach when it's loud. Okay, look. What's on top? A over B. Rate A over rate B. What is this? This is a rate. That's why it's on top. Rate A. A is the unknown because it's mentioned first. You just didn't have the book didn't give you an actual number, and I don't like that. I want you to have a real number. So I'm just pretending that these numbers that I gave you are in the book already. Okay?
Okay. But how do you know what the rate of helium is?
Because I told you the rate of helium. Do you see it? Look at the text. Look at the chat group. It's not in the actual problem, Emily. It's not there. They didn't give it to you. I don't like that. I'm giving you the actual numbers.
Okay. Okay.
He put something in there and I couldn't get it out. So I was gonna ask you about it and I forgot. All right, are we all on the same page now?
Yes.
Yes.
Okay. So here's how you solve for the unknown. It doesn't matter wherever the unknown is. X could be on the top, X could be on the bottom. This is the method to use. How do you get rid of a square root?
You square root it, I guess.
You square it.
So that would be, wait, if X is 5.50.
No. Look, ready? Sorry. These were just my labels. There's only one X in this problem. It's right here.
Okay.
I just labeled that so I knew which rate to put where. There's only one X. It's right here. We're solving for this one. We don't want this because it's really annoying. Because if that's not there, we could just cross multiply and then divide, right?
Right.
How do you get rid of it? What do you have to do to get rid of a square root? All right, look here, ready, guys? If you haven't had this in algebra yet, to get rid of something, you have to do the opposite. If we are multiplying, we divide. If we are adding, we subtract. If we are square rooting, we square. Good. So now look. What you do to one side of an equation, you must
Do to the other.
do to the other. So look, I'm going to square this entire side, and I'm going to square this entire side. See? Now, what is 4 squared? Type it in your calculator.
It's 16.
16. So it would be
Hang
on
on,
the
hang on.
left.
16 over x what?
Squared.
X
Squared.
squared. Equals, what's 4.5 squared?
20.25.
And then what's 30 squared?
900.
Wow, I chose really crazy numbers. Sorry, guys. All right. So here we go. How do we solve for x now? Cross multiply. Okay. So look, I'm going to take 20.25 times times x squared. I'm going to have 20.25 x squared equals 900 times 16, which is 14400, 14,400. All right, what's the next step? How do you get up x on its own? Jordan, we still can't hear you. So how do I get rid of the 20.25? All right, Emily Mongol. How do you get rid of something if you're multiplying it?
You divide?
You divide. So I have to divide both sides by 20.25 to get rid of this, right? So divide both sides by 20.25.
I thought we'll cross
What?
nothing.
711.1 repeating. Use the whole number in your calculator though, okay? How do I get rid of a square root?
It's frozen.
Oh, I'm sorry. Is it better now?
Yes, but I don't know.
Okay. How do I get rid of a square?
You square root it.
Square root it. All right, square root both sides. X equals 26.66 repeating.
Cool.
Right? Did everybody get that? Can you see it, Emily? Sorry.
It's really blurry. The internet's really bad at the church right now, so everything's like slow.
Oh, I'm sorry. All right. Well, I promise you it says 20.6 and then 6 repeating. And Jordan, did you retype it, but you didn't retype it with all of the ones? I don't know what you did, Jordan. We'll have to look at that in a little bit. How many significant figures would we have in this final answer? Because there are real numbers that can give you sig figs. Look at the original rates. What are they? How many? They have 3. The 4.5 and 3.30.0. Those both have 3. So we're going to do 3 sig figs. So we're going to have 26.7. And that's our molar mass. What's the unit for molar mass?
Grams per mole.
Grams per mole. That's our unknown gas.
Cool.
All right, now we could, let me see if I even gave you, I gave you fake numbers, so let me see. What's close to 26.7 on your periodic table?
Aluminum.
All right, so we would have had aluminum. That would have been our unknown gas.
Aluminum is a gas?
Yeah, I guess. They just made it a gas, I guess. I made up these numbers, so that's why this is weird, okay? But does the process of solving for an unknown, does that make sense?
Yes.
Okay.
I think if we went over this on Thursday, because I miss stuff since it's free. Overall, it seems pretty easy. Just simple steps.
I should be able to do it.
Okay, Emily, we were just having some very serious lag with you. I think that you were saying that you maybe missed some things, but that it's making sense with the simple steps.
Yeah.
Okay. We haven't covered this at all yet. Remember that this is just over the videos that you were supposed to watch before today. So you should go back and rewatch those videos if you need to, or for some of you need to watch them in the first place, okay? All right. Let's look at the next type of math you might have. And this one, before we get to it, I want to talk about gas pressure. So look at page 407. I'm typing it in right now, page 407.
Not fun.
All right. So I am going to assume that you're going to be able to do some background studying on your own. First, studying like things like what a thermometer and what a manometer, those two you have to know on your own. So go back and do some history on that. We are going to talk about units of pressure. And listen, we are going to do problems for the rest of the year where we refer back to these different units of pressure. Especially hard in chapter 13, we will be covering gases specifically. These numbers, these units are going to matter. So I need you to do me a favor. I don't need you to memorize the conversions for all of these units of pressure. I just need you to memorize the units of pressure so that you know what they are. All right, so that you can, if I were to give you a problem, you could go, oh, that's a pressure. I know that's a pressure because it says millimeters of mercury. Okay, so that is where I need you to be. And so I want you to be on like table 12.1. They have a bunch of units of pressure: kilopascals, atmospheres, millimeters of mercury, torr, pounds per square inch, and bar. Do you see that? Start memorizing those, okay? So that's something you want to be familiar with. Now, I'm going to help you remember one of these because it's James's corny joke, and I love it, and it makes me super happy. So I'm going to be telling you this corny joke to help you remember one of these units of pressure. Do me a favor, kiddos. Take off your shoes, and you have suckers.
I thought you were talking to us.
Listen, you can have it back.
It's okay.
She's got the.
I'm just gonna say if they're gonna eat them, maybe they can just sit on the
They're
sit
not
in.
like sticky. They're alright.
Yeah, yeah.
Okay, shoes. Shoes.
Sorry. You're good. Have fun, guys. Maybe you guys want to sit. I don't know. All right. So before we can understand this corny joke, we have to actually have some background history. I want you to look in your page at what a Pascal is. So look on that 407. I want you to look with me. It says specifically 1 Pascal is equal to the force of 1 Newton per square meter. So 1 PA equals 1 N over an M squared. Right? Do you see that? Can your eyeballs look at it?
Yeah.
That's what a Pascal is. That is a unit of pressure. That's a really small unit of pressure, to be honest. So we usually refer to pascals as kilopascals. Notice in the bottom how you have kPa. That's what we normally use because pascals are so small. So kilo means 1,000 times bigger. So we're usually going to refer to these as 1,000 times bigger than just a Pascal. But that being set up, here's my joke. Pascal, Newton, and Einstein are playing a game of hide and seek. Einstein's turn to be it. So he closes his eyes and goes 1, 2, 3, and Pascal runs off and hides. Newton, however, stands right in front of Einstein and pulls out a piece of chalk from his pocket. On the floor, he draws a roughly 3 meter by 3 meter by 3 meter square, and he stands right over it. 10, ready or not, here I come. Einstein opens his eyes and he goes, Newton, my good sir, I have found you. Newton says, you are mistaken, good sir. You have found a Newton over a meter squared. You found... Who did he find? You found Pascal.
That's really stupid.
It's corny. I love it.
That's great.
Corny jokes are my favorite, especially when they're corny, mathy, nerdy, sciencey jokes. So it's a Newton over a meter squared. So he drew a, 3 feet is roughly a meter.
Uh-huh.
So, he drew a meter square, and he stood on top of it. He's Newton over a meter squared. It's Pascal.
Which means he won.
Yay! Okay, so you guys are going to have to know those. Ta-da! You thought you'd never have fun in chemistry. Ha! You were wrong. All right, so next we have the type of math. So turn the page again. And we have total pressure. All right. Total pressure is going to be the easiest thing you will ever do in your entire chemistry career, as long as you remember what it is. Okay? My handy dandy bottle. Let's say I pump 3 different gases in here. I put oxygen, carbon dioxide, and helium all together.
Mm-hmm.
The total pressure will be equal to each one of the individual pressures added together. Does that make sense?
Yeah, it does.
Because each one has their own pressure, and if they're all together, it's just the pressure of all 3 of them. Right?
Yeah.
Guys, it can't be any easier. Not if I tried.
That might be my favorite law.
It's really the
It's
total
like the
pressure.
law of conservation of mass. This equals the same thing.
Yeah, pretty much. Okay, so let's read the first example. Number 4. What is the partial pressure of hydrogen gas in a mixture of hydrogen and helium if the total pressure is 600 millimeters of mercury and the partial pressure of helium is 439 millimeters of mercury? So let's set this problem up together. Ready? The total will equal the pressure of the what?
It'll be 161.
Don't give me the answer yet.
Why not? I just did it in my head.
Do you see how this is set up? The total is equal to the helium plus the hydrogen.
Yeah.
Right? What's my total?
600.
600. What's my helium?
439.
49.
We don't know hydrogen, so I'm putting an X. How do you get X on its own?
You subtract helium from the total.
Subtract helium from both sides. That's it. That's your answer.
Such brilliance.
So, 600 and sorry, I'm so dyslexic. Ha! This was 116. Oh, my word. I can't even say anything. 161, and I put 616. I'm so sorry. Anyways, that's it.
That's all you do?
All right, now look at the next one. Find the total pressure of a mixture of gases that contains the partial pressures of 5.00 kilopascals, 4.56 kilopascals, 3.02 kilopascals, and 1.20 kilopascals. Go.
3 plus 1, 8, and 5. 8 and 5 is 14. 56 plus 2, 76, 78. Is it 13.78?
What's the unit?
Pascals.
Not just pascals.
I don't.
Kilo pascals. But yeah, that's it. Did you guys get that?
No, I didn't.
All right, Emily, what did you do?
I didn't do anything. I was confused.
You were confused by number 5?
Yeah,
All right, look, Emily, what's it asking for?
it is
Hey.
asking for the total pressure.
It's asking for a total pressure. What is the total pressure?
Together.
What?
Just add everything together.
You just add everything together. Total, all of the individuals combined, right?
Yeah, I thought it was 500, and I looked closer, and that made more sense.
Oh, got it. Yeah, that's just 5.00. Okay, guys, look. Here's what I need you to do now. Solve number 6 and type your answer in. I don't want you to say it out loud, Emily. I just want you to type it in, okay? So solve and type in the answer to number 6. Thank you for the unit.
Am I done?
Patience is a virtue.
I don't have very many virtues. I'm good at eating.
That could be turned into a vice really fast.
I don't know. It's such a essential part of life. I feel like it's a pretty.
It's true.
Nope.
Emily Mongold, do you have this one?
I'm typing in.
Okay. Yes. Okay. Questions over the 2 types of math we just did. All right, look, it's time for us to be done, but listen. Thursday, you should have watched all of the videos for this chapter.
Okay.
All of them by Thursday. I know that's a lot, but you can do it a couple per day. The other thing you should have done is started work on your PowerPoint presentation.
Okay.
You don't have to have it finished. I just want you at least to have read the directions and started at least getting your thoughts together. Okay?
Okay, I've never done a PowerPoint presentation, so I guess I'll have to Google that, how to do that.
This is a good reason to start, a good opportunity for you to learn how.
Okay.
All right. Thursday, we're meeting in person. I'm inspecting your tests and your quizzes. Look, I'm not going to go over, like, this chapter is vital that you guys watch the videos carefully because I'm not going to go over the entire section for each one of these chapters. Thursday's it. I'm going to highlight the couple areas that I think are hard. I'm going to jump around between each of the 3 sections that are left, and I'm only going to stop on the things that I think are the most important. You will have to know all of the material by reading the book and watching the video and studying and doing your project. I'm only going to highlight the things that I think are the hardest. You guys are responsible to get the rest of this chapter on your own, okay? All right. Good luck. You know how to get me if you need me.
Do you have the directions for the?
I have to find out if I put them on OneNote. I'm going to copy them and paste them into Edmodo, so I'm going to try to do that before I leave right now.
Okay.
All
All right.
right.
Thank you very much.
No problem. See you.